Hello guys, myself Dr. Mahantesh, Associate Professor, Department of EC, SJB Institute of Technology, welcomes you to this pre-recorded online sessions on electromagnetic waves, Introduction to Electromagnetic Waves, Module 1, Class 5. In previous video, we had discussed about electric field of a line charge and volume charge distribution. Another basic charge configuration is the infinite sheet of charge having a uniform density of rho s coulombs per meter square, and also we will be discussing about electric flux density in this video. So we will derive an electric field of a sheet of a charge. As I told you, this is another basic charge configuration. Infinite sheet of charge having a uniform density of rho s coulombs per meter square. The charge distribution family is now complete. Point Q and line rho L, surface rho S and volume rho V. So these are the different types of charge distribution. So now let us place a sheet of charge in such a way that it lies on the YZ plane, and again consider symmetry. We see first that the field cannot vary with Y or Z. So the fields are not varying with respect to Y or Z. And then we see that the Y and Z components arises from the differential elements of charge symmetrically located with respect to the point at which we are desired to evaluate the electric field intensity. Hence, only Ex is present and this component is a function of X alone. For a differential width of strip dy dash, the line charge density is given by rho L is equal to rho S dy dash. The component dEz at P is 0 because the differential segments above and below the y-axis will cancel each other. The component dEy at P is also 0 because the differential segments to the right and to the left of the z-axis will get cancelled each other. So only Dex is present and this component is a function of X only. So now that this differential charge element is separated from the point P at the distance r is equal to square root of x square plus y square, Dex is given as rho s dy dash divided by 2 pi epsilon naught square root of x square plus y dash square cos theta. Therefore, rho s by 2 pi epsilon naught x dy dash over x square plus y square. Adding the effects of all the strips, we will get Ex is equal to line integral of minus infinity to infinity x dy dash over x square plus y square. I am going to take out the constant outside the integral function. Remember your basic integral calculus, integration of du over a square plus u square is equal to 1 over a tan inverse u by a plus c constant. So here rho s over 2 pi epsilon naught tan inverse y dash by x, the limits varying from minus infinity to plus infinity. Substituting the limits to this tan inverse function, I am going to get rho s over 2 epsilon naught. So therefore, the electric field intensity of a field of a sheet of charge is equal to the surface charge density over 2 epsilon naught. Fact: the electric field is always directed away from the positive charge into the negative charge. We now introduce a unit vector an which is normal to the sheet and directed away from it. And Most of the times it is perpendicular. Hence, it is given as E is equal to rho s over 2 epsilon naught in the direction normal to the direction A. The field of a sheet of charge is constant in magnitude and direction. It is not a function of distance because we don't have any R component or a distance component, neither in numerator nor in denominator. It happens to be in the denominator in our previous electric field equations. So now we shall discuss more about electric field, electric flux density. So after drawing a few of the fields described in the previous videos and becoming familiar with the concept of the streamlines, which show the direction of the force on a test charge at every point. It is difficult to avoid giving these lines a physical significance and thinking of them as flux lines rather than calling it as an imaginary lines or a streamlines. Now we shall try to give some physical significance and we shall call them as flux lines from now onwards. It is very helpful to invent an electric flux which streams away symmetrically from a point charge and is coincident with the streamlines, and to visualize this flux wherever an electric field is present. So about 1837, the director of Royal Society in London, Michael Faraday, was interested in the static electric fields and the effect of various insulating materials on these fields, and he was calculating electric flux density. So this is the lead to his famous invention, the electric motor. He found that if he moved a magnet through a loop of wire, an electric current flowed in the wire. The current also flowed if the loop was moved over a stationary magnet. So changing magnetic field produces an electric field. In his experiments, Faraday had a pair of concentric metallic spheres constructed, the outer one consisting of two hemispheres that could be firmly clamped together. He also prepared shells of insulating material which would occupy the entire volume between the concentric spheres. So Faraday's experiment also showed, of course, that a large positive charge on the inner sphere induced a correspondingly larger negative charge on the outer sphere, leading to a direct proportionality between the electric flux and the charge on the inner sphere. The constant of proportionality is dependent on the system of units involved. And we are fortunate in our use of SI units because the constant is unity. If electric flux is denoted by psi and the total charge on the inner sphere by Q, then for Faraday's experiment, psi is equal to total charge Q, and the electric flux is measured in coulombs, that is Q. So now we can obtain more quantitative information by considering an inner sphere of radius A and an outer sphere of radius B with charge of plus Q and minus Q respectively. The path of electric flux phi extending from the inner sphere to the outer sphere are indicated by the symmetrically distributed streamlines drawn radially outwards from one sphere to the other. So in the next class, the next video, we'll be discussing more about electric flux density and the introduction of Gauss law and divergence in the coming videos. Thank you for watching this video. Take care.